Had to unmute my microphone. Hello. Oh, Andrew's here. Hi, Andrew. Hi, everyone else who happens to be here at the moment. Welcome to the second live stream for COMP1511 this term, which is going to be talking a little bit about the second assignment, Pokedex, as well as just the stuff that we've been working on in the second half of the term. So, second half of the term's been all about pointer structures, memory management, and the implications of that being our ability to use things like linked lists. And your second assignment is very much on use of linked lists. So we're going to be making linked lists of the structures that we have. Um, Mostly linked lists of Pokénodes. That's like the main structure that we're using, but there might be useful linked lists of things like Pokemon as well. Um, so we've got a couple of people here now already. Say hi if you're here. Feel free to say hi in comments and stuff. We'll see who's around. I'll also say hi, just like I'm here. Yes, strangely enough, I'm here because you can see me on the camera. So if you're here, say hi. Um, these streams are not sort of pre-prepared or organized or anything like that. So the stream is going to be driven a fair bit by whatever questions people have who are here. So I think this one's taking a little longer to warm up than the previous one because we've only got a few people here for the moment. But if anyone has anything they would like to know about, or they would like to hear some clarification on, I'm more than happy to take questions. I'm happy for you to start off with questions if you want to, um, before I sort of jump into things in any particular way. So feel free, or you can also even just say hi if you're there, because I don't think there's anyone actually talking in chat at the moment. Um, okay, so let me start off with a little bit. One of the tutors, Alvin, was talking to me earlier, and he was saying that one of the things that people are getting a bit confused about is the structure of the structures actually in the Pokedex. So one thing I'm going to do is I'm going to pop open uh, the assignment spec itself. Oh wait, it was right there. That's week 8. No, we want to look at the assignments. All right, gonna open that in a new tab so it's easier to see. Okay, so I think one of the questions that we're getting a little bit is about the structure of the assignment. So where and how does the code that we've given you work? So I think that's one of the interesting and potentially difficult things is what happens when we drop you into a large piece of code and you have to kind of understand what's happening. So this is not something that we expect everyone to really 100% be able to do yet, but what we're going to do is give you a bit of a hand on exactly how this particular one works and sort of give you an idea about how you're going to read assignments and, well, not just assignments, but just coding work in general, and get an idea about how you want to pull it apart and see how it works. So we're going to explain a lot of it, and then in future, when someone doesn't explain a lot of it, you'll probably be able to pick up some of this yourself. Hi, Toshi. So someone at least said hi in the chat. Feel free to say hi, anyone else who's watching. Okay, so we've given you a series of files. Um, there's there's actually a command that grabs all of these files in one go. I don't think we've changed the assignment spec to say what that is, but we will at some point. Um, I do also want to, let's grab the week 8 lectures. Where are we? Week Was it week 7 or week 8 that I talked about this? That one. I'm going to view in browser, make it a little bit easier to see. Okay, week 8 lectures, I had some slides that were showing the structure of the assignment, and I think it's quite handy to have a look at that. But what I'm going to do, actually, I'm going to do two things at once. I'm going to grab the code itself and also have a look at these diagrams and show you what I mean by these. Andrew's got the link for us there. So where am I in my account right now? I'm going to go to my COMP1511 directory and I'm going to make a new directory. I'm going to call mine Pokedex. You can call yours assignment 2 Pokedex or Pokedex or assignment 2, that kind of thing, just as long as you remember where it is. I do suggest that everything you do, you put in its own directory, because otherwise things are going to get real messy. I'm not following my own instructions here with a couple of pieces of code that I just threw up. These might have even been from the last live stream. That one definitely is from the last live stream. Anyway, so let's go to our Pokedex folder and use that command that Andrew gave us. Let me make sure. Yeah, I'm typing the right thing in. Okay. In here, we now have a set of files. Note that if you are running 1511 colors, this command, this is already set up for me, but I did it again anyway, you'll see different files have different colors. These pale blue ones that are in bold are links. So you don't have the file itself. You have a link to be able to read the file. The nice thing about that is knowing that if we change the file, so if something happens in the assignment and we say, oh, we needed to change these files, we'll send a notice out if we're going to do that. But as it is now, we're highly unlikely to change those files because people have already started. So we're not necessarily going to change them, but we might if something drastic happens. We really want things to be different. Um, ooh. Toshi's asking some questions. Let me just finish this explanation, Toshi, and I'll get back to you. Okay, so these files are links to files that we have, and you're not going to make changes to those files. You're just going to be using them. Whereas the ones in white are standard files, the way we've gotten used to using them, and those files are things that you're going to write your own code in. So the majority of your own code is really going to be in this Pokedex.c. But I am going to talk a little bit today about what's in these files and how it relates to what's in these lecture slides. So we've got some information in these lecture slides about stuff like that. But while we've got a question already from Toshi, you're asking about, I'm just reading off this other screen here. Is there anywhere that tells us what we're going to cover in the lectures for the next 2 weeks? Almost finished with the assignment, but I'm wondering what C features I might not be using. So let's have a quick look here at the course outline. And this is actually be really funny because like I'm opening up the course outline and I wrote this like months ago, so it'll be funny because I haven't looked at it either. I have a different course plan that I usually use for everything, so I'm going to open that in a different browser so we can see. Um, One of the things we have here is the course schedule. So we've had week 8 already. Oh, I can't believe how fast this session's gone. Yeah, so we've had week 8 already. We did linked lists. So we've done linked lists over week 7 and week 8. And this week's tutorial is still actually going to be on linked lists. So you could consider week 9 to have some linked list work in it. The next thing we're going to look at is abstract data types, interfaces, stacks, and queues. That is going to be actually very similar to what you've used in Pokedex. But we're going to look at how we might actually build it up. I look like I've got an extra comma there. That's me not completely proofreading everything. So what we're going to be doing with these abstract data types, the Pokemon that you've been using is actually an abstract data type. So it's actually the idea that we can have a file that describes a structure, a set of files really, because it's a CNH file together. They describe the structure, but they don't give you access to the internals of the structure. They ask you to use functions instead for it. So we're probably going to build one or two of these, but as you can see that there's actually nothing in the week 9 content that you need for the assignment, other than it might help you understand the assignment and might help you understand how we actually created the files for the assignment. So we created the Pokemon files and we created the Pokedex files. And this is a particular structure that's actually used a lot in programming, this abstract data type, which is the idea that you have an idea that a data type exists. This is like, say, struct Pokemon. You have an idea that struct Pokemon exists, but you don't actually know what's in it. And you can't actually use what's in it. The only thing that you can use is like this abstraction of it, where you know that it's a magical thing, and you can call some functions. Those functions take this magical thing as inputs or outputs and that kind of thing. And they can make changes to these things. They can make them, they can destroy them, and that kind of thing. But they don't necessarily give you complete unfettered access to the data type. So this is the kind of thing that we do to protect our information from people being able to change it by accident to things that shouldn't be changed to. Um, or we make it so that the access to this thing is really easy. So if I want a really complex operation to just be a single easy function with an easy set of inputs and outputs, I can put that function in my H file and say, look, you don't need to worry about what's happening in here. What's happening underneath the hood is like triple deep while loops with all this other stuff going on. And whoever's using this data type doesn't need to know that there's that much detail. All they need to know is that we'll do a job for them. And so we put that in the H file and say, okay, this is the job that's going to get done for you. And then we call those functions without having to think about how they work. The example I like to use a lot of the time is just all the libraries that we've been using. They're not necessarily abstract data types, but they work in the same way in that we use scanf and printf, etc., and all those other functions without bothering to know what's inside them. And there's a lot of hard work that's gone into making them work really nicely, and we just make use of it. Yeah. Oh yeah. So Toshi, you've probably read through the course schedule before, right? And you had an idea that this kind of thing was coming. Yeah. So that's what we're going to be looking at in week 9. We're also getting introduced these things called stacks and queues, which are ways to use things like linked lists and arrays. And there's no particular reason why we would use a linked list or an array for each of those. There's pros and cons for each. We can use them either way. Um, but we can have an implementation of an abstract data type that is actually completely different from what we'd expect. But it doesn't matter because all we see is the functions. And we trust that underlying that is something else that tells us what's happening. So we're going to cover that in the next week. And week 9 is sort of, I would say, a time where we're looking at some advanced content that we won't necessarily be examining you on that much. Like, we will a little bit. We will test a tiny bit of an idea about how your stacks and queues work. But in terms of what we're expecting you to be able to do to pass or even excel at this subject is arrays, functions, characters, and strings, working with memory. Linked lists is a big one. I mean, like, if I do something like, we talk about linked lists started here. So linked lists started when we started talking about pointers and memory. And then we talked about structs and using pointers with structs. And you already know that that's the basis of what linked lists are. And then we looked at memory allocation, and then we got to linked lists. And when we think about it, we've actually been doing linked lists for 4 weeks. Because we've been slowly building up all of the pieces necessary to be able to learn them and to be able to work with them. So what we've got is like when you think about it, the first 4 weeks is the intro to programming. You got your while loops and your if statements, and working with arrays and characters and strings and stuff like that. Excuse me, sorry about that. I hope I didn't blast anyone's headphones just then. Um, this could be considered the first half of the course, and this could be considered the second half of the course. And this could be considered some add-on stuff, which is going to be really, really useful to you later on in programming. But we're not going to necessarily be expecting you to build these. So building abstract data types is something that we'll do later. But we do obviously expect you to use them because we've actually done that with the Pokemon, right? So we've actually given you an abstract data type and said, okay, you're going to have to learn to use this. Even if you don't fully understand it, you should be able to get some of it working just from your knowledge of functions. And a little bit that we've taught you about multi-file projects as well, about how if we call a function in an H file that we've included, we expect it to work because there's other stuff the C file implements it and things like that. So there's a bit of stuff going on there that is sort of being used, but this is us teaching you how it's actually built and things. But you don't always need to know how something's built to be able to use it. I mean, perfect example of any computer that you have, your smartphone or anything. We know so little about how they're built. There's these huge factories, like I mean, like we know that like silicon is a thing, but I wouldn't have the slightest idea about how silicon is made into a whole bunch of things that switch back and forth and like process maths and things like that. That's a level of engineering I don't understand at all. But I trust it because I trust the people that made it and I trust that it works in a certain way enough to program it. So the abstract data types is a little bit like that at the moment. We're going to get you to use it without necessarily knowing how to build it, and we're going to show you a little bit about how to build it. But if that doesn't stick for everyone, that's okay as well. It's not really, it's not something that is knowledge that we consider you have to have at the end of Comp 1511. The knowledge we consider you have to have is more like weeks 1 through to 8. So I do expect people to be able to at least do the basics of working with linked lists and the basics of working with arrays, which I think we covered in week 3 there. Okay. I think I've answered Toshi's question. I probably answered your question a little bit more because I've just like sparked off a conversation of like all this other stuff I wanted to talk about, but that's okay. So Emma has a question. Emily has a question. Hi, Emma, as well. How do you know if a Pokemon is found? So I think this question is actually quite a big open-ended question, isn't it? So we're looking at this would be around stage 3 and further. We talk about finding Pokemon. So we talk about whether a Pokemon is currently found or not. And so we have here some examples of Pokemon that are found or not found. So the not found Pokemon, we want to display them as stars, the same number of stars as their name would be there. So that's Bulbasaur, so it should be the same number of stars. And if it's not found, we don't have any information about it. So it's kind of like we have a blank entry in our Pokedex. So if I was holding my Pokedex and using it, it would be like, this is a type of Pokemon, but I don't know exactly which Pokemon it is. I don't know how it works, but if I meet the right Pokemon, then it will flick over to a different sort of state, I guess, where it will be found as opposed to not found. And when it's found, it appears differently. So this is like the metaphor for this is like Pokemon, where I don't know if you've played the game, Emma, but it's a game where you go around and then you go around the countryside and then you just randomly have encounters with Pokemon. So you go, oh, there's a a Pidgeot. Pidgeot is like the one I think this is one of the first ones you see all the time because they're just outside of town. They're like pigeons, and you meet them, and after you meet them, the entry in the Pokedex for them is something that you can look up afterwards. So you can look it up and go, oh, this is the Pidgeot. This is the thing that I was looking at. So the concept is, have you met them or not? If you haven't met them, you don't get full information. So you get something that looks like this. But if you have met them, the information should look a little bit like this. Pidgey. Sorry, Pidgeot is the evolution, isn't it? It's the first evolution of the Pidgey. I can't remember. I'm sorry. I mean, if you ask me super detailed information about the Warhammer 40,000 universe, I will be able to tell you nearly everything in that entire universe. But unfortunately, Pokemon's a different era for me, so I didn't entirely grow up with it, and I apologize profusely. I can tell you the entire history of the Ninja Turtles though, if you'd like. Um, oh, but I was right. Pidgeot was at least one of the evolutions of Pidgey. So I'm throwing out random words, and some of them are sticking. Okay, so we were talking about the concept of finding. So Emma, you were asking, how do you know if it is found? what we're going to work with in the Pokedex is in the beginning, everything that we enter into the Pokedex is not found. So we're thinking like we've given someone a fresh Pokedex, and that person has never met any Pokemon before. So when we first give it to someone, it's not found, and then it's up to the people there to go find the Pokemon, which is what we have in this stage 2 here. Wait, not stage 2, stage 3. I scrolled up too far. Stage 3 has some of our functions that reflect what might happen when people go exploring and meet Pokemon. So go exploring is one of them, and this is the one that's actually going to go through, and it follows on from show types. So go exploring is going to go and actually grab the first Pokemon that it sees of each type. I think that's technically what it does, but there's more details. In the H file has the actual explanation of exactly what it does. In fact, let's not just skip straight over that. I'm going to open my Pokedex.h. I'll just move this over so that my face isn't blocking some of the code. So about there. Yeah, that looks right. I've got another screen up there where I'm seeing what I'm streaming so that I can make sure that everything looks okay. Okay. So we're in stage 2. Stage 3. Print out all different types of the Pokemon. Each type should only be printed once. So this is the first one, which is if we have these different types, then we're going to print out the types. And then go exploring is this one. So the first of each Pokemon type that it finds that hasn't been found, it sets them to found. So this is like us walking around the world and saying, we're going to meet one water type Pokemon, one electric type Pokemon, the ones that I've got here, one psychic type Pokemon, one ground type Pokemon. Um, and so you go around and you go, okay, I found one water one, I found one electric one, and it's going to flick these over between unfound to found. Um, so I don't know how much I'm extending your question beyond what you were originally asking, Emma. So feel free to chime in if you want to. If I've already answered it, or if you want more information in a particular way, I'm happy to shift this in the direction that we're going. But the trick is that every entry in the Pokedex is related to a particular Pokemon. If I go back to, did I click that properly? It was in the lectures here. So the Pokedex is here. This is the overall structure that has the head pointer in it. So you'll notice that this is slightly different from my lecture examples. My lecture examples, the head was in the main, but this time the head is actually inside a struct of its own. And this is so that we can have more than one Pokedex if we want to, and also so that we can keep other information about the Pokedex itself. So there's other things in the Pokedex that I might want to put in here. I'm not going to give it away, but maybe in some of the stages there might be something you want to put in the Pokedex struct itself. So this is information that pertains to the entire Pokedex. But when we're looking at individual things, we've got a head pointer that points at the first element of the list. These elements are allocated somewhere in memory. You may have to do that. I'm pretty sure that's part of stage 1 to create the list itself. And each one of these has an entry, and that's a Pokenode struct. And each Pokenode struct has a pointer to a Pokemon struct somewhere. So you won't even really be working with this as a struct. You won't be working with these details in particular, but you will have something that creates a Pokemon, which is type def, which is like equivalent to this struct, and then you use the functions to access the information. Um, so Emma's asking, in stage 1, it says add a field to struct Pokenode to indicate if a Pokemon has been found. Do we just do that in stage 3? I would say that yes, that's probably not a bad idea. Oh, hang on, Tom. Oh, right. So it's actually before stage 3. If we were like, Tom's reminding me that there's actually stuff earlier. So stage 1 has adding and printing. Add Pokemon. I think the find Pokemon function is in here somewhere, right? Do, 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 do. Struct Pokenode. detail Pokemon, get current Pokemon, find current Pokemon. So, couple of details here, right? So the current Pokemon is like if we have a whole list of Pokemon. I'm gonna start drawing. Xpaint. Okay. Oops. Width 41 is gonna be too big. Width 4 is okay. Okay. So I have a list of Pokemon, and when I'm thinking about this as a Pokedex, what I have is, yeah, sure. Oh, I wanted that to be text. Oh well, whatever. Pokemon 1. Let's not. Let's. Yeah, I'll just do it. Okay, Pokemon 1, Pokemon 2, Pokemon 3. So this is it. Okay, we're just going to 1, 2, and 3. I was thinking about giving them their proper names, and I realized I'm typing with my mouse, and I'm not going to do that. I should actually just use the text thing there. Either way, um, what we're looking at is if we were using the Pokedex. So if I had the Pokedex in my hand and I'm going through, I would have the list of Pokemon, and I would be selecting them with like a cursor. So Pokemon 2, maybe. Or, oh, it doesn't undo. I just wanted to delete that. Anyway, where's my eraser? No, no. Yeah, I'm too used to. Oh, I can undo. Yeah. So if Pokemon 2 was the current one selected in the Pokedex, that means that this would be Pokemon 2 here that I could get some information on. Or if I want to set it to found, I would say, okay, go to that Pokenode for that Pokemon and say, okay, this one is now found. So actually, add a field to struct Pokenode to indicate if a Pokemon has been found. That's actually a stage 1 thing now that I look at it. So if this one here becomes found, then its name will then appear in the list, that kind of thing. This current Pokemon is an arrow that can move up and down the list. So stage 2 is navigating the list. And in stage 2, we're going next Pokemon, previous Pokemon, and that is the thing that's going to move this arrow up and down. So as I do next or previous, I can change which Pokemon is currently selected. And if I say find current Pokemon, that's going to say that whichever Pokemon I'm currently looking at, that one is going to become found. So I need some way to figure out which one of these is found. There's going to be a bit of detail there on deciding how to reference which one of these is the found one and isn't. Um, Before I give stuff away, Andrew, you've got videos on this, don't you? Let's see if Andrew's got. I'm pretty sure. Yeah. Ah, so you do have a find Pokemon video. Did you use a pointer in for that one, Andrew? I'm just wondering whether I should say stuff here about the recommended implementation for this, or whether I'm just going to give away too much by doing things. Because I've seen this implemented in different ways. Cool. Um, I'm going to give people a small amount of help here, in that if we have this selecting a certain Pokemon, I could very easily have something. Hang on. I'm just going to switch colors. From a code perspective, I could very easily have something that's really similar to that arrow. Um, this is currently selected, Andrew, and then we're going to talk about found as well. So if I have an arrow pointing at a certain entry in this list, I could also have an arrow pointing at one of these Pokénodes if I want to. And so just dropping a huge hint here at what I would consider to be an arrow pointing at a piece of data in the memory of my computer, it's highly likely to be something like a pointer if we want to. And then if I did have this, and this is the current, oops, let me, um, I'm going to do that in the same color. So this is current. This could be a way to reference one of the elements of the linked list. And I think if you've been paying close attention in the lectures and stuff, you should know that there's a way to reference a variable that's already been created in memory. I'm using all the keywords around it except for the exact word for it, but I'm pretty sure people will pick it up. So if I had a way to reference that, then I would want to say, if I want to make Pokemon 2 found, I could take the current Pokemon, and you can think about where you might want to store this variable that accesses the memory location of another variable. I'm just giving it away. You have that. That accesses this, which means you'd be able to get access to the fields in here, which means you could change something in here. So, for example, in here, what if I had a thing in here called found? Yeah, this is totally to scale. I don't know how that ended up down at an angle, but you know, we live with it. I'm living with my wonderful art here. So if I had a field in this Pokenode, so let me just make this clear. These are Pokenodes. So these are all struct Pokenode, and they're all together in a linked list. So I could access the current to get to one of these, depending on which one in my theoretical menu I was looking at that point in time. And this isn't even that theoretical, this menu, because you can press P and it will print out all the Pokemon in the interactive version, and it will actually have an arrow. I think it's on the other side. It'll have an arrow telling you where it is. So then we could change this found field in here by accessing the current and going into the Pokenode to the found field. So here, I think there's a suggestion that found should be added, right? Somewhere. Yeah. I know it's somewhere, but I don't know exactly where it is because there's a lot of text in here. Oh no, it's back in stage one. Yeah. Oh, cool. Yeah. No. Tom and Andrew were letting me know that there's actually a forum answer for this. So someone's written out a fairly detailed um, response to this as well. So if you need to, if one of you wants to post a link to the forum, I mean, like some people want to see it with diagrams and stuff like that, but I mean, chances are if it's been answered on the forum, it's probably been answered with diagrams as well. So there's probably a lot of information there. So we'll get that link up depending who gets to it first. Tom's here with me and Andrew's at home. Sorry? Oh, Tom's not actually on the stream right now, so he's relying on Andrew to pop up links. Okay, so that's the kind of structure around setting the current Pokemon to found. When we get to stage three, Emma, because Emma's also referring to stage three, when we get to stage three, it won't necessarily just be the current Pokemon that's getting set to found. That's for current Pokenode, sorry, that's getting set to found. We might be going through the whole list of them and setting a bunch of them to found. And so we want to see you able to loop through a whole list of Pokenodes, check conditions against the ongoing conditions, I guess, of the exploration that's happening and set a few of them to found. So that's why stage three is harder than stage one. Stage one's like, okay, just set the currently selected one to found. Okay, so I'm going to scroll back up because I've been talking to Emma for a little bit, but there were other questions that were asked in between. Sorry? Yeah, and I think Lorenzo up here was asking a question as well. Lorenzo says, "Hi, I have a question. Are we allowed to use int arrays for the function get Pokemon of type? I think a tutor on the forum said we could, but the order tests fail automatically if you include them." So, oh, we have changed that. Okay, so one of the things, yes, Lorenzo, it's a good question because what we were doing was trying to get you to obviously use linked lists for Pokénodes and Pokemon if you need to have linked lists of Pokemon and stuff. So basically, all of the assignment specific structs need to be in linked lists. They won't be put into arrays. So one thing we don't want you to do is just put all the Pokénodes into an array of Pokénodes and then bypass all of the linked list stuff because like the whole design the assignment is designed around. Oh, you're welcome, Emma. Hopefully that helped. Yeah, the entire assignment is designed around getting you to use linked lists, so teaching you a lot about using linked lists. So we don't want to have people circumvent that and use arrays and accidentally not learn anything about linked lists, because that would be like a whole month worth of the course just sort of wasted if you don't actually put it into practice. Um, However, if you do want to make an array, we're talking about an array there of get Pokemon of type. Get Pokemon of type is our stage 3 thing, and you wanted to use int arrays for that. We can actually use int arrays for that. So, as far as I know, we have changed that. So, where are we? Actually, I'm just going to go back to the spec. Get Pokemon of type down here, where we might. I'm not sure exactly what um, array you're using there, but I assume it's an array that goes along with the list of Pokemon types. So you're just making an array that's exactly the same size as the number of Pokemon types there are, and you're referencing that or something. Oh, you meant show types. Show types, Go Explorer, right? Okay, no, that's cool. Yeah, so we're looking at Go Exploring. So you're looking at this part here of, say, for example, um, having an array of all of the um, all of the different types there are, and then using that to decide whether or not you've already seen a type before, you've already shown a type before. Yeah, as you say there, Lorenzo, to hold previously seen types. Yeah, that's okay. Um, so if you're using an array of integers inside your functions, that's totally fine. The only thing that we don't want you to do is to um, put your Pokénodes into an array, because then you're not going to get any practice with linked lists. And as Tom was saying a moment ago, we have just um, lowered the kind of the strictness of the way that the auto tests and stuff work on that. So we'd started off with it a little too strict, where we had the auto test saying that if you make any arrays in this, we're just going to make you fail. And we decided that, especially for things like this, there were some good solutions that we considered to be elegantly programmed solutions that were using arrays here, and they weren't causing problems for the learning that we wanted you to have with the linked lists. And so that's more open now. So if you want to, you can potentially, Lorenzo, you can potentially go back to your previously submitted versions if you've done Give before, like if you've been saving um, on our system like that, you can probably roll back to a previous version and grab the code that you had that used the array and see if it's now accepted. So it might be okay. Hopefully you haven't gone way out of your way to make a completely different solution for this and made it really messy, but you should be able to use that array stuff if you want to. Yeah. Oh, right. Um, as in the audio is. Sorry, Tom's just telling me. Oh, yeah, 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 yeah. That's fine. Yeah, yeah. Tom's just reminding me that the stream is like half a minute behind what I'm actually saying here in the room, so I should um, give people enough time to answer me. Oh, I apologize, Lorenzo and Toshi. But you know what you did learn from that? I'm just trying to salvage the situation. What you did learn from that is how to find a way around a problem when you're constrained. So in this case, yeah, it's a little bit silly because yes, you could have used arrays for that and you would have gotten a reasonably nice solution out of it. But what you did learn from that was how to work within constraints. So you get these really, really funny things happening when you're out there in the world and you're programming and stuff. And you get weird constraints put on you because it's like, okay, this just doesn't work like this. Let's find another way around it. Or the system we're working in doesn't work under certain circumstances. If we load up the CPU beyond a certain point, it drains the battery and it stops running. Um, and so we need to find another way to like slow our code down. We have weird constraints. Like this actually has happened with like embedded systems and stuff. I had a friend who was working on a system that had to go down to Antarctica, and they had to be really, really careful. Like the temperature became a real issue, and so they had to work with cables that couldn't drop below a certain temperature, and if they dropped below a certain temperature, their networking would stop working, and so they had to keep um, I can't remember exactly how it worked, but they had to keep systems running that would keep warming up the cables if they wanted to use it and stuff. And so there's all these other things. And so you'll find that like even though yes, it would have been for both of you easier to just use arrays at that point, what you've done by accident, and I apologize anyway for it, is you've accidentally learned how to find a way around a problem even with a constrained um, set of capabilities, and that's actually a really, really valuable skill. So I'm just trying to twist that around so it sounds like you learned something useful there. So hopefully that's not too bad. Hopefully you don't hate me too much for lifting that requirement a little bit late after you'd already worked on things. Okay. Um, Toshi's saying, yeah, challenger exercises and random constraints on the assignments have been really nice for learning things like linked lists. Okay, well that's good. I'm glad. Um, a lot of a lot of programming is not about writing code to make code work on computers, which is ironic because it seems like a lot of programming is writing code to make code work on computers. But a lot of programming, and I say a lot of programming, is trying to figure out how to solve problems within a system. So C is a system. It is a massive system. It's got so many moving parts in it and stuff. But when it comes down to it, it's a little machine. We can think of it like a Rubik's Cube. A Rubik's Cube says you need to get all these colors in the right places. The only things you can do is twist these things in certain directions or spin the whole cube around to look at it from a different angle. That's all you can do. So it's a system, and you need to use that system to solve a problem one way or another. And strangely enough, Rubik's Cubes are still really hard to do. Like some people have learnt the algorithm that just solves the whole thing, and that's fine. Um, C is the same thing, and programming at a much bigger level is also the same thing. So programming is the idea that we can move things in certain ways, um, and using the ways that we can move things, we want to get a certain result. And so the logic behind trying to figure out how you're going to move things based on what you have available is like one of the core things about programming. So that's when we talk about problem solving. And I give you a lot of practical means of problem solving. It's like, okay, figure out what you can do, figure out what changes you can make, figure out the smallest things you need to do that get you closer, and then sort of save them and then move on to the next thing. That would be like solving one face of a Rubik's Cube before you try to figure out the others. And then when you try to figure out the others as well, you go, okay, now there's constraints I have to manage between things. And so one of the things that we've been trying to teach you in Comp 1511, and it's very kind of it's nearly underneath the surface teaching that we give you, is can you deal with a system that just gives you a certain number of pieces you can move, and can you solve all kinds of problems with just that minimal set of pieces? And that's the kind of skill that I think is like one of those long-term skills. So I could nearly say, I don't necessarily want to say this, but I'm going to say it anyway, that learning how to program in C is sort of useful, but may never be used again. There's some of you who will never do C again after this. But if you've learned something about how to solve problems in difficult situations, there's no way that's not going to come up again, right? That's definitely going to come up again. It's going to come up again and again and again in your life. And when I think about that, when I think about teaching people how to program, that's what I'm actually really trying to teach. Um, so I don't mind if like you don't like C and it's like, yeah, C didn't agree with me, but what I did learn from this was how to solve problems, how to solve abstract logical problems in different ways by approaching things based on what can I do, what can I shift in this system to make things work. Anyway, that's just a bit of a random talk. This is what I like about the live streams. I have time to talk, so I can actually just talk about things like that. Okay. Oh, people have been talking to me during that. Yeah, Lorenzo says no worries at all. Oh, you like the first challenge question without the if statements. That's the order three challenge, and I also really enjoy that. And you can see how there's a lot of that stuff that we give in the challenge questions, which is like, okay, we have not given you the means to do this, but underneath we have given you the means to do this. We haven't necessarily told you how. So there's this thing that happens with humans. Uh, if I was to give someone a hammer, the thing that you think about when you've got a hammer is that you can hit stuff. So you think about using them on nails, and it's this thing that humans do where we call it functional fixedness. It has a scientific term where um, once someone's holding a hammer, then everything looks like a nail. They'll just start hitting stuff with it, which is not always the best thing. Uh, the same thing happens with programming. I give you a while loop, you think everything needs to be looped over. And it's like, well, not everything needs to be looped over. We can just we can just work on some things without a loop, or we can use other ways to move through content rather than always looping through them. Except for the moment, I think most of your stuff is going to be looping because that's we've structured it so that you can actually learn loops. But people don't always realize that you could use a hammer as a weight. You could use a hammer to balance something. You could use a hammer to prop something open or closed. You could use a hammer to jam into space between two other things just to keep them apart and stuff like that. And that's the idea that we could give you something and say this is how to use it, but the side effects of using it could be much more than just like an if statement or something. It could be more than just a yes or no, or it could be more than just something that loops and things. There's many different ways of doing it. That was sort of revealed last week in the lecture when I used a while loop that didn't touch any of the elements. It just moved through, but it stopped at a certain point. Instead of thinking about always covering everything in the loop with the while loop, I said, no, I don't need to cover everything. I want to stop when I find the right thing. And when I've stopped, I have a pointer to the thing that I've found. And then suddenly the while loop has another purpose. So it's not just look at everything. It's multiple things like that. So I hope that that kind of thing has helped you see that uh, everything that I'm going to teach you has a purpose that can be used for its purpose. But once you realize that C in itself is a really, really open, um, uh, a really, really open tool that can do lots of things, you can actually shape it to do the things you want. Um, Toshi's saying, yeah, with that while loop something that you ended up, oh, that's great. You ended up using that in your assignment. That's really cool. Um, and it was eye-opening. That's really nice to hear. So you'll see that, and then you'll see like depending on different programmers. And this is another thing that I also say a lot, but I'm gonna keep saying again while we've got people here listening. Looking at the way other people code, super useful, because you'll see a way that someone does something that you didn't expect and you didn't know before. So the whole idea of code reviews. If you haven't already, there's not many chances left. If you haven't already, throw your code up for code review in the tutorial. Then at least you can sort of put your code out there and then see what other people think about it. And maybe someone else can say, oh, I've got a different way of solving that problem. And you can learn something new about looping or something like that. So, okay. that's that's all an aside, but I think quite valuable nonetheless. We had another question way back before I started talking to Lorenzo and Toshi about functional fixedness and things like that. Bilal Khan is asking, what is Pokemon type? I'm trying to print the type in the add detail function, and when I try to print the type, it gives me an error that I should use the D specifier. Okay, let's pop into the code. I think it's in the C file, isn't it? Or is it in the H file? No, it's in the C file. Wait, it's in the Pokemon files. Sorry, I'm just going to get my chat up to where we are. So, I'm just going to go for C. This is the types in strings, which we don't need so much. But here is the Pokemon type. Yes, you can see this, but there might be another way to use this. But Pokemon type here, this is something we haven't shown you. Um, because we weren't necessarily using this C construct that much, and it wasn't something that we considered that you really, really needed to know to be able to code in C. Like you can see how like what we do is we're trying to teach you exactly what you need to know to code well in C, and we're trying not to add too many extra things on the side that would cause problems. But what these are very similar to this. That's why we don't teach it to you because we don't necessarily need to. So this thing called an enum is going to go through all of these and basically, it's not exactly, but basically is going to do this hash define. So hash define none type is 0, normal type is 1, fire type is 2, etc. So if you're going to use one of these as the all caps types, what you're going to get is they're going to be exactly the same as a hash define, so they're going to be very similar to a number. So if I say fighting type, so 0, 1, 2, 3, I'm going to get the number 3 every time I use this all caps fighting type. So it's very, very similar to doing a hash define for each one of these things in this list. It's just an easier format here that we can use. Um, so if you're trying to just print this out, like so, like fighting type, what you're going to get is it's going to try to print out a number. You don't necessarily want to print out that number though, right? Because when we're asking you to do the question, hang on, let me scroll back up to the question, was the add detail function. So let's go add detail. Is it add detail? There must be a different name. I'm going to look up detail. Oh yeah, it might be print details. Print out the details. Oh, it's detail Pokemon. I'm going to assume that that's what you are looking at. So, detail Pokemon is supposed to print these things out, and I am assuming that the issue you're having is that when you try to print out the type, you're putting in this, for example. So it's a, let's just say it's a fire type Pokemon, and I go, okay, this is fire type, but if this is the case, hash define fire type is 2, then it's going to try to print out the number 2. And if it's trying to print out the number 2, it's going to just put a 2 here in the type instead of the fire type. But what we want to do is make sure that when we print it out, we're printing out the correct um, type of it. And if I remember correctly, here in Pokemon.h somewhere, clone Pokemon, Pokemon ID, Pokemon name, Pokemon height, Pokemon type, first type, second type, Pokemon type functions, Pokemon type from string, Pokemon type to string. Ah, isn't this interesting? Let's read what this function does. Return the string name of a given Pokemon type value. So, this is the beauty of having something like an H file is, how long did that take me to find that function? That was like 10, 15 seconds of scrolling through the functions that were available here. I see there is a function here that says if I call Pokemon type to string and I give it a Pokemon type, so you did know the Pokemon type, right? So, but um, Bilal there was asking, yeah, I have the Pokemon type and I'm trying to print out the type. How do I actually get that to something that prints out properly? It could be that what we need to do is just transfer this into a string like so. So Pokemon type to string. This is an example of a function name that nearly gives me everything I need already. Because it's like Pokemon type to string implies, okay, I'm going to give it a Pokemon type and I'm going to get a string in return. Don't worry too much about the const there. Const is something we haven't talked about. It's a keyword that most of the time means this thing will be a value that doesn't change. It won't give me a variable, it's just giving me a value. I'm not going to go into const because const has like 8 different capabilities depending on where it's used in things. So we're not going to talk about it too much. But the trick that we're getting here is this is returning a string. So if it's returning a string, that means Pokemon type to string takes in a Pokemon type and returns a string. And so we're getting this nice combo here where if I call this function, that should translate for me the not that one, this one, this one here, which is actually a series of numbers, into the corresponding string. And if you want to look closely at how that works, it's actually in here where it says, all right, if you gave me flying type, I'm going to give you the word flying. You give me grass type, I'm going to give you the word grass, that kind of thing. So that's going to get us to the point where we don't have to worry about printing out a string. There's already a function, there's already a capability in Pokemon H that does that for us. And it's down here in these Pokemon type functions to convert them back and forth. And you might actually want to use this at some point where you can take a string here, character pointer is a string, and then convert that into the number Pokemon type. So, Bilal, I'm not sure if that answers your question, but I think that's a fair bit of information around it that says that if I was to try to print out the actual Pokemon type, which is up here, this actual Pokemon type, yeah, it'll be a number. And that number, it'll try to say in a printf, for example, that I should have used a D because it's a decimal integer, in the same way that I would print out an integer. However, if I want this to be a string and I want to print out the words for it, I should actually convert it to a string, and then that should, with a bit of effort of figuring out exactly what you were going to do with that string afterwards, you can probably then print out the string for it instead. So there's a little bit of work to be done, but should be possible to do. Okay. Um, yeah. Tom's reminding me we're about halfway through, so let's take a quick break now because I've actually covered I think all of the questions that we had in the first hour. So we'll take a quick break, and then what I might do is obviously if people have more questions, I'll definitely answer the questions in the second hour. But I might also step us through some of the basics of the structure of the assignment, so where things kind of appear in memory and how they work. And also, I did have a really interesting question after one of the lectures. Someone came to me and asked me why certain things were happening. So I might actually step through something that happens in one of the functions in the lecture code and show pictures of what actually happens in memory when those things are happening, like how we actually join lists together and stuff like that, which might be useful to people. So we'll see how that goes. Anyway, let's take a quick 5 minute break. And we'll be back and we'll talk a little bit more about linked lists and structure of things and draw some pictures as well. Alrighty, let's get back into it. So, I wonder which one I want to do first. Um, so Alvin, one of the tutors, was talking to me about some questions that he was getting, which was, I think the main question was, what is, where is it, Pokedex.h? I don't think it's in the H. I think it's in the C that I'm looking for here. Yeah. Just opening the Pokedex.c file. So I'm opening a bunch of stuff here for the assignment. He was like, what's this versus what's this? And that's a pretty interesting question. It's a pretty valid question when you have these two things. Except in lectures, I never had these extra structs. I only had one struct. And that struct was this one. The one with the information in it and the next pointer in it. And everything that we'd been doing with linked list was just pointer to the next and some payload data, which was either an integer or a string, depending on which example we were looking at. Here we have something more complex because we have a Pokemon, and if we look at, I don't think it's here, it'll be in the Pokedex.h, that Pokemon is a pointer to another data structure somewhere. What I want to do is show you what this structure is, which is why also I had this open. So this is what this means. The linked list is not sitting in our main. The linked list is sitting inside a struct. And the struct itself can be created in our main. So if I want to create a new Pokedex, I should be able to get that structure. So if we look at this, actually, if you look at the create Pokedex, oh, that's new Pokenode. New Pokedex. Here, we've actually already done this for you. We allocate the memory for a Pokedex itself, make sure it's not null, and we say there are no Pokenodes in this, so the Pokedex head is null. We've also said you are going to need to make your own code here. But the trick is, really, that when we say new Pokedex, we get given a Pokedex, and a Pokedex is a pointer to that Pokedex struct, basically. So what that means is my main, if it calls new Pokedex, is going to get one of these structs. And then if I want to add nodes to that, I'm going to have to call other functions. And strangely enough, they're going to be in here, new Pokenode. So if I want to add a new Pokenode to my list, I call new Pokenode, and actually it's not even there. I think create Pokenode is something that we're going to do here. And then when we get into these things, add Pokemon is going to use these other functions. That's why they're outside of stage one, these other functions. You still need to do stuff with them. But add Pokemon is going to say, I have a Pokedex and I have a Pokemon, and what I'm going to do is I'm going to add a Pokenode for that Pokemon to my Pokedex. The way that happens is I take my list of Pokenodes here and I just add another one. I'm pretty sure if I remember correctly, the whenever we add a Pokemon, it always just goes on the end of the list. So we're not worried about you having to insert in order here. We do that later with other stages, but we're just inserting something onto the end of the list there. Which means if it's the first one, it gets put here with a head pointer pointing at it. And note these are not inside the Pokedex struct. The linked list is in its own memory, so each node is memory allocated separately, as we will see. Use a new Pokenode function here. It's not been implemented actually, so you have to do that yourself. Yeah. Um, but we can probably guess that if we're making a linked list, and the linked list is going to need to last beyond, for example, this function, because we definitely want the linked list to last beyond that function, we're going to have to memory allocate for it. And so this diagram kind of makes sense if we consider the entire slide to be the memory for our program. The Pokedex struct sits in memory and it has a head pointer in it. That head pointer then has access to the first Pokenode. But these Pokenodes are just somewhere else in memory. The only relationship they have with the Pokedex itself is the Pokedex has access to the first one, and then we follow their next pointers along to get access to the rest of them. We can add information to the Pokedex. I'm not going to say anything more. The more I say, the more I'm just going to implement your assignments for you. And That's actually one of the funniest things you can do to a programmer. I've done this to Tom over there before, is you just ask them a complex question and you imply in some way that they can't necessarily solve it, and then like 2 hours later they're like, that's really mean. I forgot to eat. But here's a cool solution. And that's the funny thing. That's the thing that you'll find as you get into this stuff more and more is like what I was talking about in the first hour about abstract problem solving, the Rubik's Cube effect. I've just made that up. I don't think it's called the Rubik's Cube effect, but it feels like it. Is that once you get excited about something, once you start getting into these systems and making changes in these systems to make stuff work, uh, it becomes something that's actually very enjoyable. It's like I can find a solution to this problem. So you can just throw these funny little problems at people, and they go out of their way to be like, how do we find a cool solution to this? How do we find something that's going to be interesting that solves this problem? Oh, Tom saying nerd sniping. Yeah, showing a nerd a problem, causing to stop whatever they're doing. Um, yeah, this is a really funny thing that happens to people if you can distract them. Well, it's not that funny. It's actually one of the major causes of inefficiency in the workplace for programmers. If you keep asking your programmers to do different problems, and every couple of hours you ask them something different on a completely different topic than what you asked them before, and then you end up with zero productivity out of the programmers in general because like they're just constantly switching ideas to other things. Anyway, okay, back in here. This is our linked list. So a linked list comes from a head pointer, which comes from inside a struct, which is different from how the basic examples that I've been teaching in class had been, where the head pointer was just out here in the main. But otherwise, it's no different, and the linked list is no different. All we have is this extra struct that allows us to say, if you want to access the Pokedex, the actual list of Pokenodes, it's inside this other struct. So the difference between these two things is the Pokedex is the thing that gives us access to the linked list, and the multiple Pokenodes are the actual nodes of the linked list. So the oh, you found the actual comic. Andrew's found the actual XKCD comment about the nerd sniping. Um, let's actually no. I'm not gonna. I just clicked on it and I was like, no, 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 no. That's exactly. It's happening right now. I love it. Okay, so I'm not going to look at the nerd sniping thing. You can look at the nerd sniping thing later. Okay? Or you can look at it now. That's fine. You can look at it now while you're listening to me talking, because since this is a live stream, you can actually go back and read things later anyway. Okay, so the Pokénodes themselves, and I've talked about the Pokénodes a little bit before, should also. Oh, this is classic. This is a YouTube live thing. I should shout out to my main man, Andrew B, and his YouTube channel called Andrew. It's called Andrew B1511. COMP1511, I think. I've sent you a link to this anyway. It was in an email notice that went out, and the notices are all on the course webpage anyway. Series of videos that go through in detail um, a lot of the ideas around how the Pokedex assignment works. And so a lot of this is going to give you some theoretical grounding. So if there's anything you're not sure whether you fully understand or not, check out those videos because he goes into pretty good detail. I think there's a little bit of advice on how to structure your code as well there. We don't really want to write code for you. I've made that mistake before of writing a little bit too much code that solves the assignment, and that's not that great. Because you know how I said that like my one rule at the very beginning of term. I'm gonna say this again because no one will have remembered it because it was like 2 months ago and no one remembers anything at the start of the term. Um, my one rule was that no one takes the educational opportunity away from anyone else. So that was the one rule. So things like, you know, harassing other people so they don't feel comfortable in class is like taking their education away from them. So it's like the stuff that I really don't like. The other thing that takes people's education away from them is giving them the answers. So if you've got all the answers, then a lot of the impetus to actually work hard enough to to learn it and to go through the process from not knowing to knowing can be ruined if you got the answers. It's like getting spoilers. Um, if I tell you everyone who dies in Game of Thrones and which episode they die in and which season they die in and then what happens and who sits on the Iron Throne at which time and stuff like that, then there's like sure there's some point in watching it, but like it's taken a whole lot of the flavor out of it for you. And so, obviously, in comparing my course to Game of Thrones, I'm saying that it's really good, but maybe ends really badly because, because you have to do an exam at the end and it's really painful. But anyway, I saw a Halloween costume of someone, and all they had was just like a placard on their chest saying Season 8 Game of Thrones. Anyway, um, those of you who do the challenge exercise this week, I actually did a Game of Thrones reference. That's the one little Game of Thrones reference that I've made this time. Um, what was I gonna say? Yeah, yeah. So spoiling stuff for people, telling people what the solutions are before they get a chance to work it out, is like spoiling stuff for them. And it it sort of means it's actually worse. Like just spoiling a TV show for someone is like, oh, what a pity. I didn't get that entertainment. But spoiling stuff for people in an educational sense is like 10 years later, you're like, I still don't know how to do that thing and I missed my chance to learn it because it got spoiled for me, and I really don't like it when people do that. So if you can, try not to spoil things for people. Like just treat it the same way as a TV show. It's like this will be cool when you get to it. We'll talk about it when we're done. When you've done that bit as well, then we'll talk about it, and then it's cool because after that you can be like, oh, we took a completely different thing from that. So it's like you can be like, ha, that Jon Snow guy. How about how he knows nothing? And then like someone else is going to be like, what? He knows nothing. I didn't get that from the TV show at all. I thought he knew everything. And it's like, yeah, well, okay. But in some cases you could be wrong. Uh, anyway, so I can't remember how we got into that, but yeah, no, I was just talking about stuff. Okay, so this is the structure of it, and what we're doing is the only thing we've added on is this little extra bit here. Okay, so one other thing that I wanted to talk about, which was a question I got after after Wednesday, I think. So if it's after Wednesday, let's look at the code. After Wednesday would be lecture 15. So this was a question about linked lists, especially because like at this point we were doing the insert alphabetical. So the insert alphabetical was the idea that we were going to use part of this function, insert alpha here. I wonder if I can try to do this without cutting off code. No, not going to be able to. I just wanted this line, just this one bracket to go back up into its own line. That's okay. We'll just leave it there. Just bear in mind that these brackets, as you can see, they don't have line numbers. They're actually from the line above. So insert alpha is going to do two things. First, it's going to find the position in the list that we want to insert in, and then it's going to call insert function in that correct place. The insert function was here, and it was going to insert a player into this. And there was some confusion about exactly how this was working. So let's step through and talk about it, and then I'll do some diagrams for what happens in different situations. So we get a pointer to the head, which is the current player. This is the pointer that's going to be moving between the nodes in the list. And we're also tracking a previous. There's different ways of doing this, by the way. This is just one way of doing this. I tried to do this in a way so you could see that I was moving two pointers at once. Um, I'm going to get rid of these. I didn't save those. Anyway, you can just roll back to screenshots if you want. So I'm just going to get a canvas so I can just draw things a little bit here. So same kind of thing. No, I want more line, make it easier to see in case anyone's on low bandwidth connections. So I got this linked list. I'm gonna you know what I'm gonna do? I'm gonna do this linked list like it's actually in memory. It's like completely random. Well, it's not completely random. Your computer at least tries to do a bit of um, a bit of organization, but there's no guarantee at all of organization of where things are in memory in a linked list, because you could be calling these at different times, and there's just memory might be next to each other, might not be, and so that one's pointing at null. Let's give these some values. I'm just going to give them numbers. So there's a 5, 8, 10, 15, 25. All right, these are in order because the way that this thing works assumes that things are in order. I've got my head pointer here. Let's see if I run out of space while I'm doing this. Okay, I've got my head pointer here. So my current pointer is going to be this purple one, is a copy of the head pointer. So current player is equal to head. Current player is equal to head, which means if it's a copy of something, then it's aimed at the same thing. I'm going to use orange for my previous pointer. My previous pointer is pointed at null. It's not the same null, by the way. I'm just pointing at the word so I don't have to write it in again. Anything that's pointing at null is not aimed at memory. It's aimed at non-memory. That's the same thing. I just said the same thing, but you know what I mean. So if it's pointing at null, it means that there is no memory location that this pointer is aimed at. So let me just write here, current is purple, and previous. Previous is orange. So I'm just going to leave those words there so you can just remember as I move these things around that's what those are. So previous is pointed at null. That's that line of code there. Current is pointed at head, which is that there. So the loop is going to go through and it's going to stop whenever it reaches something that was alphabetically correct. So we were using string compare there. I've put numbers in here, so it should be reasonably easy to see with the numbers when this thing is going to stop. So let's say that my magic number that I'm using for this, I'm running out of colors. I'm going to use a cyan. The magic number that I'm trying to insert is 9. I'm just going to put a 9 there so remember it. So this is the node that I'm trying to insert in the list. So what I do is my current starts looping through the list. The current is not equal to null. Current is not equal to null. So it's going to go into the list. Let's say this compare is saying that I'm going to keep looping if the number I see in the current player is less than or equal to the number I have in my value. So this is a similar kind of comparison. We were doing it with strings. We're going to do it with numbers here. So 5 is less than 9, so we are going to go into the loop. So since 5 is less than 9, we're going to go into the loop, and previous is going to equal to current player. Let me get my eraser here. So previous is no longer here. It is now equal to current player. So it copies the current, which means it's aimed at the same thing. Then the next thing, current player then moves on to current player next. So if it's going on to current player next, and this is currently current player, and this is the next pointer, which means that the current is no longer equal to what it was equal to before. It comes over here, and current is now equal to next. So this is the movement of the 2 pointers. And so they're going to move again, because that while loop just ended, and we go back to the while loop here. Current player is not equal to null, and for the moment, because I'm doing this with numbers, 8 is less than 9, so we're going to keep moving. So in order to keep moving, we do these 2 commands again. Previous is equal to current player. So previous here is equal to current. If a pointer is equal to another pointer, then it gets moved. Oops, no, wrong color. It aims at the same thing. Then we say current player is equal to current player next. So current player is no longer equal to this, it's equal to the next of this, which is aimed at that one. So this is the way pointers work. Pointers access memory by saying this is the location that I'm aimed at. So if I set a pointer to something new, I set it to another pointer, that means I'm now pointing at that other thing. So this is the movement of the two pointers here. And then we go into our test again, but now 10 is higher than 9 rather being less than 9. And so we say, oh, okay, this is where we are now, and now we would call the insert function. So this while loop would fail. These will not change again because we never enter the while loop if the condition in the while loop fails. So we never run that. We jump to here. Well, not never. We've run it a couple of times already. We're not running it there. We come down here and we insert in the right place. And so the insert function, if we go back to the insert function here, create insert new player into the list that starts at the head. Oh, no, wrong comment. It's this insert player. Insert after. So we're inserting after a certain node, and we're creating a node of that kind. Okay, so insert after is after the previous. So that's not bad. We know that previous is currently pointed at 8, and we've said insert after 8. So insert after is going to do a little bit of pointer manipulation, and it's going to grab this thing. I'm not doing it in exactly the right order, but basically it's going to grab that thing and say, this linked list pointer comes down here, and then this one has a next pointer in it, and it's going to come out here and join up there. And that's what the insert function is going to do. And then it's going to return the head of the list. So that's the simple case of that working. So now we have a full linked list with the 9 in it there. But one of the questions that I got about this, which was quite interesting, was like, what's actually going on with these other cases here? So what happens if previous is equal to null? And right at the end of the lecture, I changed this to link up the head and things like that. So let me start a new diagram to show you this other thing, because it was actually quite an interesting question. I thought it was worth looking at because it looked at the theory behind the fact that linked lists are all sort of any node with a pointer in it is a linked list. Any linked lists can be joined to each other just by moving pointers around. So I'm going to put that one away for a moment, open a new canvas. So what happens if previous was null? And what does it mean if previous was null? So let's say I have this list here. And it has the values 8, 10, 15. And this time the value that I'm trying to insert is 7. When I go into my while loop here, I'm going to use some of the same colors. When I go into my while loop, I should actually have the head pointer there. If I go into my while loop, my current is pointed at the first one because that was set up before the while loop. My previous is pointed at null. So my previous was orange. I'm going to make that null red. So my current is the head of the list, and my previous is null. What happens if I'm going to insert 7 into this list is that it's not exactly the same because this one's comparing strings, but if we're comparing numbers, this one fails the loop immediately. If it fails the loop immediately, then this never runs. So these instructions never run, and we skip to the end of the loop, and we come down here and we insert. So what happens if I insert into this previous here? I'm inserting into a null list. So I'm inserting into a list that's empty. So what's going to happen if I do that insertion here into this is the following. Over here, let's put a nice box around this. This points at null. Because this was empty, this doesn't have a memory location. So I'm not inserting wherever this pointer was pointing because this pointer is pointing at nothing. So I've just created a new one. And I have something when I create this, which is the insertion point here, which is the output of this function. So I'm going to find another color. For this one, you can be green. I'm going to call it IP because that's not a confusing internet term at all to use IP for something. Anyway, the insertion point here is now a pointer that points at this. So the issue that I get here is like when I ran this at that point and I left it like this, it would output one thing and it wouldn't output the rest of the list that it was trying to insert in front of. So if previous was null, we inserted at the start of the list. I had, I think this line wasn't in it. I just had the head is equal to the insertion point. And the head is equal to the insertion point gets us this far. So I can take my head pointer there and say, instead of the head being here, so instead of the head being here, this is the head. It pointed at this one. So I said, yeah, cool, we've inserted at the start of the list. We've inserted at the start of the list. It's here. Only when we inserted it into an empty list, which means there's no list afterwards. So one of the things we needed to do is do this bit of code here. Insert point next is equal to head before we set head to insert point. So let's step back in time for a second. Gonna undo. It's gonna have to undo all the letters that I've reached the limit of undo. If anyone was working on the undo stuff in CS Paint, you can see that the redo undo buffer for this was not very large. Okay, anyway, the head pointer, I'm gonna have the name head here, running out of space. The head pointer was initially pointed at 8. So what I want to do is I want to say insert points next is equal to head. So insert points next is this pointer here. If this is going to be equal to head, it means I'm going to aim it at the same thing that head was. So it's no longer pointing at null. No longer pointing at null. If it is pointing at head, it means it is copying the location of the head pointer, and it's saying my pointer is also going to aim at the same thing, which looks a bit like this. And this is how linked lists get messy in memory. After that, the head is equal to the insertion point. So the insertion point is this 7. So the head says, I'm no longer pointed there. I'm now pointed here at the insertion point. And notice what this looks like now. I mean, sure, it's messy and it's all over the place. Head points at this element of the list. This element points at this element of the list. This one points at this one. This points at this one. Sorry, that one should point at null because it's the last thing in the list. We now have a completely valid list that I've inserted something at the beginning of. And also, what we've done here is we took a new list we created out of nothing. So we had 2 separate linked lists. The head was pointed at one linked list. The insertion point was pointed at another linked list. And then what happens is we actually joined these 2 linked lists together. So that's the cool thing about this is we could take one linked list that only had one element in it. We can join it to the other linked list, and then suddenly we have a complete new linked list that's made up of 2 other linked lists. And you can actually do this. This could have had like 100 elements in it. And I could have just taken the last one that was aimed at null and aimed it at that list, and it just joins them together. And then we have one big long list instead. So this is something that like, it was really funny because I just had this conversation with 2 students outside the lecture afterwards, and I realized that this is like a really, really interesting thing that we could look at that might be really useful for people's understanding of how we actually move these pointers around and how we get an understanding of linked lists. That diagram perfectly represents what it feels like to manipulate linked lists in your head rather than on pen and paper. Are you saying because it's like all complicated and messy and stuff, if you try to do it in your head, you have no understanding of what's going on? I'm not sure. But yeah, hopefully, yeah. And then this goes over. Oh wait, where's that? Oh, look at that meme. You have you seen the meme of the guy who's just like, wait, where's the camera? Um, I need this back over here a bit. Yeah, he's like, yeah, and there's conspiracy theories on the wall and stuff like that. I need that meme for describing how to make linked lists work for people. Um, but hopefully it's not actually the finished diagram that does this for you, but it's the step by step as I went through and I moved things around and how that relates to the code. Because I think this is honestly, I think this is the hardest thing about linked lists. The hardest thing about linked lists is to take this thing, which says, okay, I can move these pointers around, I can attach these pointers to different things, and then you go over here and go, wait, what? How is that that? And I think that's one of the most difficult things is how is that that? And that's a matter of practice. So that's a matter of saying, okay, over here we have a specific syntax for things. We have an order of things from top to bottom or to top to the bottom with a loop and back and forth that says these instructions go in this order and these things, then these equals are the same as me moving, erasing this and changing it to a different position, that kind of thing. So going back and forth between the diagram and the code is something that's really valuable to know how to do. Um, One of the things that I suggest, and also because linked lists are something that you will learn how to code now, and in 2 or 3 years' time, you'll be like, oh, they're easy. It's just pointers and memory. You just move it around. It's no big deal, right? Because you've actually moved on to much more difficult things than that. Except the core concept here that's really important is to be able to go back and forth between these things. Like, do I have an understanding theoretically of what I'm doing? And then can I translate this into this other language? So this is still kind of, I mean, Toshi's still laughing at me, but this is human understandable here. That a human can understand how these things work. You don't need any particular um, sort of knowledge of programming to be able to go, okay, I could follow these things around and I could join these things together. I mean, you have to have some concept of what null is, maybe, and stuff like that. But otherwise, you could say, okay, going to move these things around. But then the second you come over here is where we jump from general human understanding of how we might connect boxes together to how do we specifically tell the computer how to do this. And so this is an understanding of a concept. This is a translation into a foreign language. And that's going to be, I think, some of the big differences that's going to happen. And that's the skill that one of the skills that we're teaching. Because I said before, what we're teaching is programming, which is like how to solve problems. That's here. But the other thing we're teaching is uh, can you talk to a computer? And talking to a computer involves syntactically correct programming languages. So for the moment, I mean, like by the time that you reach a certain point in your career, you might be sitting down on a couch and having a conversation with a little speaker thing, like an Amazon Alexa or something like that. You might just be having a conversation with them, and that might be what programming is at that point in time. We might reach a point where computers are so good at understanding what we mean when we're trying to explain this diagram that they code it up and we don't. But for the moment, we're still here. We're still here, and until a whole lot of us get really good at this and do really good things with this, we won't yet reach the point that we can just have a verbal conversation with the computer and then it does whatever work we want it to do. That's kind of the holy grail of computing, if we can get to the point where we don't actually need programmers anymore. It's really funny. Millions of programmers working as hard as we can to try to make ourselves completely redundant and no longer needed in the industry. So look forward to fun times and lots of programming until there's suddenly no programming anymore. Um, I don't know. I don't know when or how that will happen, but I'm pretty sure it is in our future. So yeah, this is this other skill, right? Take this theoretical, and those of you who oh wait, it's Monday. No one's had their tutes yet this week, but in tutes this week, there's probably going to be a bit of this going on. There's going to be a bit of talking through the diagrams and stuff, and in the labs there'll be a bit of this, right? So we want you to see both and be able to translate between them. I encourage you also when you're working with linked lists is to always draw stuff. So one of the things when I'm helping students individually is like at some point during the conversation, there's always a point where I say, "Hey, do you have a pen and paper available?" I prefer using the student's pen and paper so you can just take it home rather than me writing it down on my own paper and then you don't get to keep it, right? That's not as useful. So usually I'll take your pen and paper out and I go, "Okay, let's draw up this kind of diagram and give you a chance to see um, how exactly this stuff should work." And then you can go back and code it. But the translation between them is really important. And so I think for a lot of the lab exercises this week, I would suggest get yourself a pen and paper out and do some stuff on paper that says, okay, I have a full understanding of how this should work, and then go to the code and then try to code the stuff that you were drawing. And you can also get to this point where you can scan through the code and go, this happens, then this happens, then this happens. You go back and forth to the diagram. You go, that's not what I drew. There's something wrong with the theory of my code. So that's I've made a logical error because I didn't follow the plan in the implementation. And that's the kind of thing you can learn about. And as you get better at that, you start to make less of those logical errors, less of the errors where your planning didn't come into your code correctly because when you've got a diagram that you've just drawn right next to you, it's really easy to see what you want to do. Um, we're going to keep doing these over the next few years as well. When I say we, I mean you. I'll probably still be teaching COMP1511 and introducing new people to these things, but you will be drawing these and they'll be more and more complex. I'm just going to make this as this and this, and there's another pointer in there going there, and there's one here, and there's one that just goes back, and yeah, anyway, let's it's just like someone just joined the stream then. They're like, what? What? Don't worry. But yeah, having things like this, and then you will actually grow to understand them, and there'll be some really cool stuff. Hi Toshi, just breaking your brain. But the deeper you go into computing, this is like totally valid. What I've just drawn here is like having more pointers inside something to point at other things. There's use in that. Okay, I'm gonna close that now because it's like it's quite messy, and no, we're not gonna save any of those changes. Um, okay, I think I think I've reached the end of actually the content that I wanted to show because I wanted to show that little example there of what actually happens here with linking stuff up because I thought it was pretty useful to know about what was happening with those insertions. Um, and the structure of the assignment that I wanted to go over as well, and a lot of the questions. So let's just check if anyone has any final questions. And also, while we've got some subject admins here, if either of you think there's anything else that I should talk about that might be of help for the assignment or learning link lists and stuff, we do actually have 20 minutes left. Otherwise, I'm happy to wrap it up uh, if people have gotten what they need out of the live stream and they're not interested in any other content, I can wrap it up there. Oh, Toshi's asking, is there any way to test memory leaks outside of using DCC leak check? Um, yeah, for what we're providing for you now, not necessarily. So I think that one thing that you're probably wondering about there is DCC leak check only tells you what happens at the end. Like you'd actually get a lot more information if you could stop your code at different points and find out if you've leaked memory at that point. You could try that actually. You could try just putting return one at different places in your code and seeing if there's leaked memory at those points. That's hard to say though, because if you put it at a point in your code where you just haven't cleaned the memory, then it's just going to say this thing you haven't cleaned, even though you're going to clean it later. Um, mm, Yeah. So Tom's advice is, yeah, unfortunately, Toshi, there isn't necessarily a way to test memory outside of leak check. There will be. You get deeper into programming and stuff, and you use different compilers and things. There's other ways to check for memory leaks, or you use a programming language that cleans up all your memory for you. But that's a different story. Um, any programming language that makes stuff easier for you in some way is usually just going to expect you to do more with it. So it's like if you stuff that I've done in the past is using game engines for things. They don't bother about memory leaks so much, but then like you won't be asked to do a tiny little thing in the command line. You'll be asked to build an entire 3D program and like do a first-person shooter in 2 hours, and it'll be like, okay, the tools will kind of reflect that. But anyway, in this course, not necessarily, but later on, definitely there are other ways to do it. There's also depending on the systems you're using, some things will actually do real-time memory checking. So there are some programs that will show you like on a screen, you can actually see the memory use and then the memory flicking on and off as you use it and you free it and stuff like that. And if you look at it carefully, you can see a block that's allocated, and it will actually maybe sometimes change color and say, okay, this bit just lost its pointer. There's no currently active pointer in the code that's aimed at this block of memory, and it hasn't been freed. Um, we don't go into that because all of that stuff is quite complicated, and at this stage of the of your degree, we really just want you to get the basics going, like just get code happening, not necessarily go into the full-on interactive debugging thing. But stuff is available. You can actually research it if you want to. There's a couple of things that you could look at. Um, yeah, 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 yep. Mm. Okay, two things that are pretty handy, and like this just came through from Andrew. DCC is using a thing called Valgrind. Valgrind is actually the thing that is telling DCC whether memory is leaking or not. You don't have to know how to use it. But it's the kind of thing that you will potentially use in the future to do memory checking and things. So it's what would you call it, Tom? It's a compiler tool in a sense, or is it? It's not really compilation. It's a runtime tool. Yeah, yeah. So it's actually something that you can sort of in a sense insert into your code so that it runs alongside your program and it can check your memory at multiple points in the program. I haven't actually used it much manually myself, um, but okay. So Tom says if you really want to use Valgrind, you can ask him about it. So if you want to get into this deep level of this and you think you've got enough spare time to do it, post on the course forums, ask for Tom and ask for some information about how to do active memory checking. I'm putting quotes up here because I know there's going to be a better term for this, but I'm just calling it that for now. Um, but one thing that you should do is not necessarily rely on the checking of things, um, but ensuring that you don't leak memory in advance by being really careful about how you declare it. So when you write code, it's really obvious to know when you're grabbing memory because you have to malloc. You have to call the function malloc to grab memory, which means that every time that you call malloc, that's something that you have to free later. So one thing that you could do is every time you do malloc, you've got somewhere else in your code like a free function or something like that. Or for example, a destroy Pokedex function. And this destroy Pokedex function um, is in here somewhere, and you have to implement it. So what you could do is everywhere else you malloc, so everywhere I'm going to memory allocate something, every time I write code for memory allocating something, I come down to this isn't actually the function itself, wherever the function is actually made. I think it's later on. Is it? Or yeah, because I think these are just the prototypes of the functions, not the actual functions. But anyway, wherever that function is, you put a comment in there saying, I allocated memory for this somewhere else in my code, or I allocated memory for this in this function, or um, this is a Pokemon, and the Pokemon needs to also be cleaned out of memory before I can destroy the thing that's pointing at the Pokemon, that kind of thing. So if you just keep track of everywhere that you think you allocated, when you go to do something like destroy, you go, okay, this is the chain of things that I need to get rid of. So it's like there's the Pokedex. The Pokedex has Pokenodes. The Pokenodes have Pokemon. So in order to destroy this, I can't just call free Pokedex. If I call free Pokedex, yeah, it'll free that memory, but then there's a pointer hanging off that aimed at the Pokenodes. And so none of the Pokenodes will get freed out of memory because I've just destroyed the pointer that aims at them. So I need to actually go into the smallest thing and free all of them and then go back up until I can free the thing at the top because I know I've freed everything underneath it. And if you, every time you create something, you go, oh, come in here and go, right, I know that I created Pokemon. Pokemon have to be freed in some way. Um, I know that I created Pokenodes. Pokenodes have to be freed in some way. And so, do I have other functions that are going to do that for me that I can use, or do I need to do it all in this function? You know, so there's a bit of planning that you can do there that can nearly alleviate the need for DCC leak check. It's technically possible, theoretically possible, to never need to run DCC leak check because you know that you have freed all the memory that you allocated. I mean, I'm going to say it's technically possible, but it's like I prefer using the tools. It's much easier. Yes, Tom's telling me it's technically possible to believe that my code will compile, or will run without me having to compile to see whether it's legal C or not. But obviously, those are very difficult things. But it is a good idea to remember that every memory allocation must be freed, which means anywhere where malloc appears in my code is a potential memory leak, and those are the places that I need to check to make sure that everything I've malloced is freed. Um, it's the same thing as like I was talking about cleaning your room, where if you don't think about freeing the memory until you've finished writing the program, it's like cleaning up your room once a year. It's really, really messy when you go to clean it. If you were to clean your room once a week, which I already know this is a lost cause. I know no one's going to do this. I mean, some people might, but not very many. But if you cleaned your room once a week, it would take so little effort and there'd be so little to do that it would just, it would feel like it's not work. And that's what you can do if you write your freeze alongside your mallocs every time. But if you malloc like eight different structures in all these different places and some in loops and stuff like that. And later on, you go, okay, how do I free all of this? You've got this monumental task ahead of you. So the trick is to sort of record what you're doing as you're doing it so that you know exactly what you want to do when you're freeing it. Um, yeah. Okay. So Toshi's going to potentially ask you some info, Tom, depending on how much time and effort assignment two takes. Okay, I think I think we should probably wrap it up there. I think I've talked about a whole lot of the things that I wanted to talk about today. Um, and hopefully I've given people some food for thought in terms of exactly how theoretically that linked list example I did last week did, how that worked, and also some stuff about Pokemon C and H and memory management, all that kind of stuff. So yeah, hopefully this was helpful. Hope everyone has an interesting and enriching experience building their Pokedex. And also, if you do need more info, we've already had the shout out. It's already still there in the chat. The YouTube playlist from Andrew B. But let me just go back to the course homepage. I have here assignment 2 Pokedex video content. So this is one of those things, which is the stream link here, which obviously if anyone's watching this now, they found this link. But there's also this playlist of videos here, which is Andrew B's playlist, which is definitely worth checking out. So there's an overview of all these kinds of things. It says 19T1 because we used a version of this assignment in 19T1 as well. Some of the stuff is still relevant. Some of the stuff that you can see here is not available to you because we've changed some things in the assignment. So yeah, so there's like, this is all still relevant and useful video content that you can use there. All right. No, what's that? Tom has asked me if I've ever heard of Newton's third law of memory management. What's that? Oh, for every malloc, there should be an equal and opposite free. That's from Shank, who you'll potentially meet him in the coming years because he does a lot of subject admin work and tutoring work, and so you may meet him later on. Anyway, we'll wrap it up there. Thank you everyone for coming along, and I assume that people are also going to view this later, so hope it's useful. Oh, that's the thing I was forgetting to talk about. That we were going to talk about exam stuff. Um, the exam is in two sessions, a morning session and an afternoon session. Sometime this evening, I will be sending out a link for people to make a preference for which um, exam they want to sit. They want to whether they want to sit in the morning or the afternoon. Anyone who has a clash with another exam, so if you have an exam on the same day, you would have been already pre-allocated to the morning or afternoon that doesn't clash with uh, the timing that our exam is. Did that make sense? With the timing of the Clash exam. Um, but anyway, that's coming out soon. Hopefully within the next few hours, we'll have that sent out to everyone to let you know that um, you can assign a preference to morning or afternoon sessions, depending on, I don't know, if you think better in the morning or the afternoon. So everyone that actually turns up for the 9 a.m. Thursday lecture is probably going to pick morning. Other people are going to pick afternoon. That's fine. But yeah, that notice will come out soon, so I'll send it out through the normal ways where it'll turn up on the web page as well as being emailed to you. Okay, sign off there. We'll see everyone Wednesday afternoon for the first lecture for this week. See you later.